Looks like we got everyone in from the waiting room. So today we're going to do applications of determinants. Pair that code with COH, HEZ. First thing is a review from yesterday, or I suppose from Monday. Find the determinant of this matrix A. I'll give you 3 minutes. Oops, let's try it again. There we go. All right, looks like we're on the right track from the responses. To do this, remember that the first thing you need to do is choose a row or column that has really easy values. I'm going to choose this middle column because of these zeros here. I then need to find the cofactor of each of these numbers, except really these zeros, it doesn't matter what their cofactor is, because whatever it turns out to be, I'm going to multiply by 0 will give me 0. So I really don't need to compute this one or this one. So I only really need to compute this one. To find its cofactor, again, you eliminate its column and its row. And the 4 numbers you have left, you need to find the determinant of that matrix. Remember, to find a determinant, you cross multiply and subtract. So that'll be 2 minus 12 and negative 10. If you check the sign change, or if you think the checkerboard pattern, plus, minus, plus, minus, plus, I'm going to multiply -10 by +1 so its sign doesn't change. So then the determinant of A is going to be 0 plus -10 times the element that created it, 1, plus 0, which is -10. And you can double check that with the calculator. Questions on the bell work? All right. Here's what we're doing today. We're going to start applying determinants to a whole bunch of different stuff. There's actually more stuff that I cut out because I don't know, I've never found it interesting. So you can use determinants to find the area of triangles. We'll start with that. That's not too bad. Use determinants to determine whether or not 3 points are in a line or whether or not they're collinear. That's the same difficulty as A. Use determinants to find areas of polygons, also about the same difficulty. And then really the most important thing is to learn how to use Cramer's rule to solve systems of linear equations. Besides this, if you're interested in 7.8, you can also learn how to use matrices to perform transformations of shapes like reflections, rotations, and translations. You can also, if you're interested, learn how to do some basic encryption stuff, and cryptograms with matrices. That's kind of cool. Getting into writing stuff in code and how to crack code languages that other people use. Okay. First one, area of a triangle. The area of a triangle that has these vertices is the absolute value of a half of the determinant of this matrix, where you take your points and you plug them in. X's go in the first column, Y's go in the second, and then you just put 1 in the third column. The book Kaiser walks you through the proof of this method. It's a log walk for a small drink of water. So I have to not to. If you're interested in why this works the way it does, you should check out the book. It does a really good explanation of it. All right. How are we doing? Does anybody need more time on this slide? Are you ready to see an example?
More time, please.
Okay. I figured that's fine. So as we get closer to the end of the semester, I suppose, looks like how the schedule is going to work out for us is we'll do 7.6 on Friday. When we come back on Tuesday, we'll do 7.4. That finishes chapter 7. It's so that Thursday next week will be a review day. And then I'll open up the test in WebAssign on Monday of the last week of school, the 25th. And you'll have all week to do it. It won't be due till the 29th.
I'm good, thanks.
All right. Let's do it. So here is my triangle that I want to find the area of. So if I call this my bottom left point, my first point, it does, again, it's arbitrary. It doesn't really matter. X1 would be 1. My first y value would be 0. X2, 2. Again, I chose this second one to be my second point, second X and second Y. Again, doesn't really matter. Third X is 4. Third Y is 3. So then I'm going to compute a half of the determinant of 1, 2, 4, 0, 2, 3, 1, 1, 1. And technically, I'm going to take the absolute value of this answer. And I usually don't write that in the book, put a plus or minus in front of that improperly, which I didn't like either. But I mean, at the end of the day, you know the area can't be negative, right? Area is a positive number, always. I shouldn't say always. But at least for our purposes, it will be. When you get to calculus, you'll start seeing how we could define negative areas. But all right. To determine what this determinant is, you could use the calculator, but this one is probably small enough and easy enough. Do it by hand. So I'm going to pick a row or column to use, and I'm going to pick the first row here because it looks like it has really easy numbers. And again, I don't need to find the cofactor for 0, but I do need to find the cofactor for the others. So to find this cofactor, I'm going to eliminate its row and column and find the determinant of 2, 1, 3, 1, which is 2 minus 3, or negative 1. And then I also need to do the other one. So if I find this one's cofactor, eliminate its row and column. 2, 2, 4, 3. That'd be 6 minus 8, so that's negative 2. So this determinant will be negative 1 times 1 plus 0 plus negative 2 times 1. Note that the signs didn't change in either of our cofactors because of that checkerboard pattern. It goes plus, minus, plus. So you would multiply these by positive 1. Their signs don't change. That gets us what? Negative 1 minus 2, so that's negative 3. So that my area will be a half, or really a half of negative 3, which is negative 3 halves. And then the absolute value of negative 3 halves is positive 3 halves. So 3 half square units, or units squared, is the area. Bo, 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 bo. So you can see it's really not that bad to use this system. And to be honest, it's probably easier than trying to find the area of this the traditional way, because the traditional way to find the area of this triangle would be to do base times height, right? So I would need to find, for one of these, how long is this diagonal, right, using the distance formula, and then what point would this be to make a 90-degree angle here, and then how long is that 90-degree or that height, right? So that's actually a lot of fiddly algebra 1 stuff that you would have to do. But if you know this, you just take your x values, make a column, y values, make a column, 1 for your last column, find the determinant, which will never really be challenging because at worst, we could always just use this last column to find it because it's a bunch of ones. All right, anyone need more time on this slide? Or have questions, concerns? Isn't that great how in math there's just like all these, like, here's a problem. I could show you 6 different ways to solve that problem. You can't do that with a lot of other disciplines. All right, your turn. Find the area of a triangle whose vertices are listed 0, 0, 4, 1, and 2, 5. 3 minutes. All right, looks like we got a lot of agreement in the answers on how to do this. So if I take my x values 0, 4, 2, y values 0, 1, 5, and then 1, 1, 1. Find the and remember you're going to take the absolute value of this. Find the determinant. Again, probably this first row is the easiest one because these cofactors will be multiplied by 0. So I end up, I don't need to know what they are. To find this one's cofactor, eliminate its row and column. You've got a 2 by 2 matrix. Cross multiply and subtract. Again, this is in the top right, so that's a positive 1 that I would multiply 18 by. So basically its sign doesn't change. And so the final determinant would be 0 plus 18 times 1, because the element that created it was 1. And so that's 18. All right, if I plug that back in, so I get a half of 18, which is 9. So the answer is 9 units squared. Hey, that's not that bad at all. Go ahead and imagine trying to find the area of that triangle using your traditional methods. Or think back way back to your honors geometry or geometry days when Miss Waters or myself taught you the shoelace method. That is not, I mean, this is so much easier than the shoelace method. Okay. Questions? All right, so next thing we're going to do is collinear points. So you'll notice this looks very similar to what we just did. The idea here is 3 points, x1, x2, y2, x3, y, x sub 3, y sub 3, are collinear if and only if this determinant is 0, which should make perfect sense to you, right? Right? If you think, if my lines are collinear, then the area of a triangle that these 3 points would make would be 0 because it's not a triangle. If they're not collinear, right, then you can make a triangle out of it, and then this determinant will have a answer to it, a non-zero answer to it, right? It'll have some area. So the only way that this determinant can give us a 0 is if the area of this triangle is 0, and the only way that could be possible is if the 3 points don't make a triangle because they're all in a line. Isn't that cool? Doesn't that just blow your mind to ever think that the area of triangles and collinearity can be linked concepts? My wife's in the other room doing something for her job, and her mind is blown. All right. Move on to the next slide. Does anyone need more time? It can take a moment to pick your jaw up off the floor from this startling revelation. You thought this was going to be a normal Wednesday, and then you wake up and find that collinearity and area of triangles are actually related concepts, and you can use the same matrix determinant method to find each of those. I say that now, but if you think like back in the 1700s, 1600s, or whatever, when this was first found, that person must have been like staggered to go to their colleagues and say, you know, that same formula used to find the area of a triangle, you can apply that to determine whether or not 3 points are collinear. And they would have been, no, impossible, show me. And then astounded. Okay. All right, so then you try it. Are these 3 points collinear? You tell me. 3 minutes on the clock. All right, looks like we're in agreement again that these are not collinear. If we find the determinant, -2, 1, 7, -2, 1, 5, 1, 1, 1. Probably the easiest would be to either use this column or this row. I'm a big fan of rows, so I'm going to use this row. To find this one's cofactor, eliminate column, eliminate row. Okay. -2, 1, 5, 1. And that would be -2 minus 5 is -7. But hold up. You check your sign. It goes positive, negative, positive. So I need to multiply this by -1 to really get 7. That's my first cofactor. Doop, doop, doop. Second cofactor right here. Eliminate, eliminate. -2, 1, 7, 1. That's -2 minus 7 equals -9. And again, I'm not going to change the sign on that one because it goes positive, positive, positive in that checkerboard pattern. Last one. Eliminate, eliminate. Gets -2, -2, 7, 5. So that'd be -10 plus 14, right? Because it's -14 minus 2 negatives make a positive. So it'd be 4. But because this is in a negative position, I need to multiply it by -1 to get -4. So that gives me my 3 cofactors. I will then multiply each of those cofactors by the element that produced them, which is all 1s. So it's a pretty easy one to do. So that'd be 7 plus 1 plus -9 times 1 plus -4 times 1, which is 7 minus 9 minus 4, -6. Right? 7 minus 13. Yeah. No, I don't. If I was doing this then as a triangle, I would have 2 more steps to find its area. I would divide this by 2 and then take its absolute value. So it turns out that these 3 points are not collinear. In fact, they make up a triangle whose area would be 3 square units. Questions? Isn't matrices fun? I told you that this whole unit, this part of half of the unit is like everyone's favorite part. Because it's just like fun math. It's fun to write. I enjoy writing matrices out and doing the math with them. All right, let's do parallelograms. Parallelograms is actually fairly easy. The area of a parallelogram with these 4 vertices, note how the vertices are, you do have to kind of do some setup work to make this run through a matrix fairly nicely. But if you do the setup work, then the area is really easy to find. You need to move one of the parallelogram's coordinates so it's at the origin, and then align one of the sides of the parallelogram with the x-axis. Actually, I'm sorry, that second part doesn't have to happen. It's just you have to move it, you have to translate it so one of the vertices is at 0, 0. Once you've done that, then the 2 adjacent vertices, A, B, and C, D, you make a matrix with those 2, and then you find the determinant of that and its absolute value. The last coordinate doesn't actually matter what it is. So again, there's a picture on the next one, but to show you an idea. So the idea here is you put one of the vertices of the parallelogram here, and then this point would be AB. This point would be CD. And again, this last point is technically A plus C, B plus D. Not that I really care. Because all I need to do is use these 2 adjacent vertices, make a matrix with those two, and find it's the determinant of this 2 by 2. Note again that you'll take the absolute value. So really technically the formula looks like this, but it's really gross to write absolute value determinant, right? Like it's not clear. Am I visually looking at it? It's not clear what you're doing as it is just to put it in the directions. So this is another thing. You can see the math here is actually going to be fairly easy. So this is another type of problem where if you see it on the ACT, you can try to solve it the traditional way if you remember how. But if not, just use a matrix. Because the traditional way does have some hiccups, because remember, you have to do you have to define one of the sides to be the base, and then you need to find the perpendicular height, right? You don't want to actually use this length. And usually they'll just tell you the side lengths, like this is 3 and 5. So you end up having to do like some Pythagorean theorem work to find out what this perpendicular height is. Or perhaps you're really spiffy and you remember that there's another formula where you can do P times Q divided by 2. So ultimately, I feel like just having a bunch of tools in your toolkit where you know how to use each one will save you on the ACT when you only get a minute. That way you can look at the problem, figure out what it's asking, and saying which is the best method for doing it. Traditional, like base times height, where I need to find the height, or multiply the diagonals and divide by 2, or use the coordinates to make a matrix and find its determinant. All right, I think I stalled long enough. Does anyone need more time on this? Okay. Boom, boom. All right, so find the area. Nice thing about this one is it's already set up so that one of the coordinates is 0, 0. So then that would tell me that this is A, B, C, D. Set up the matrix. 2, 0, 1, 3. 6 minus 1 is 5. So 5 square units. Did I mess somewhere up? No, times 0. I'm like, that's not right. 1 times 0 is 0. Who said 5? Get out of here. And you can check, since this is actually is a fairly simple one, you could do this the traditional way really quickly. It has a base of 2 and a height of 3. And if you do 2 times 3, you get 6. Isn't that kind of weird? You would have thought, like, if I would have just asked you at the start of class, which figure needs a larger determinant to find, a triangle or a parallelogram, you probably would have said the parallelogram because it has more vertices. But it turns out you only need a 2 by 2 matrix to do a parallelogram, and you need a 3 by 3 in order to do a triangle. All right, anybody need more time on this slide? Sweet. All right, yeah, I'm not even going to do a practice problem on that. Most important thing today, save the best for last. Kramer's rule. The solution to any system of linear equations is the determinant with respect to your variable over the original determinant. And again, you'll do as many of these as you have variables. So if this was just a system of two linear equations, you're really just going to do dx and dy. If it was three, then you would do all three of these. If there is four variables, then you'd have to do a fourth one, right? All right, what do these things mean? D is the determinant of the coefficients. It must not equal 0. If it equals 0, then there is either no or infinite solutions. Okay, I already did that. All right. What these variables are, dx, dy, and dz, is the determinant of the matrix made from substituting the constants in for your variable's coefficients. So basically, you're going to find, if it's a 2 by 2, you're going to end up finding 3 determinants. If it's a 3 by 3 or 3 systems with 3 equations, you're going to end up finding 4 determinants. And to be honest, when you do these, I would just expect you to use your calculator if it's a 3 by 3 or higher. For a 2 by 2, 2 equations with 2 variables, you could probably get away with doing that by hand really quickly. But after that, doing 4 determinants, 4 3 by 3 determinants, it's almost certainly going to be faster just to do it in the calculator. You know what I should do? I should make all of these slides interactive, and I should just have like a green button on it that you can like drag a smiley face to or something, so that once you're done writing, you just move your face to the green button. It sounds good in practice, but there will be someone who went AFK and they haven't done it, and then I'll be like, hey you, hey, are you here? Are you ready? So I don't know. Anyone need more time?
Yes.
Okay, that's fair. Kramer's rule. Well, I'm going to end up showing you 4 different ways to solve a system of 3 equations with 3 variables. Kramer's rule is about half of the class's favorite last year. Inverse matrices is probably the favorite. This is probably second place. But I mean, you can only really use inverse matrices because of Kramer's rule in the first place. So, and we'll do that inverse matrices tomorrow. Or, yeah, tomorrow. All right, how about now? All right, cool. Cool. Let me show you an example. So this. So what I'm going to do is I'm going to take this and I'm going to set up basically 3 matrices. D, the traditional is a matrix, remember, of the coefficients. So my coefficients are 4 and -2, 3 and -5. And again, x is going one column, y is going the other. Find this determinant, I would cross multiply and subtract. That's D. All right. D sub x I find by replacing 4 with 10 and 3 with 11. I take these constants and I replace them in the matrix. So this will be 10, 11, -2, -5. So again, you start out with just the coefficients. Note that this is not 0, so that means we do have a solution. If this was 0, then we would either have no or infinite solutions. Next, I find d sub x by replacing the x column with the constants here. And then I cross multiply and subtract. Is that? I think that's that. It is. Okay. One more matrix I need to do is d sub y. Again, I got two variables, x and y, so I need to do a d sub x and a d sub y. To do c sub y, I'm going to replace my y column with constants. So, I'm kind of doing this grossly. These should all be determinant symbols. Not that it really matters, but they should. So 4, 3. And again, instead of -2 and -5, I'm going to put 10 and 11. Cross multiply and subtract. 44 minus 30 is 14. All right, so then that means my solution, if you look back, last step is I'm going to divide these. Those will give me my coordinates. So my solution will be -28 divided by -14 and 14 divided by -14. So my solution is 2, -1. That is where those two lines intersect. Again, for a 2 by 2 like this, you might think, hey, it's easier if I just use substitution or elimination. But, or I suppose you could also be like, I'm going to use the Gauss-Jordan system that they taught you in 7.3. But I don't know, as you practice this, it's pretty quick. You're just doing cross multiply and subtract, cross multiply, subtract, cross multiply, subtract, and then division, division. All right, questions about this? Or anyone need more time on this slide? All right, the last thing I want to show you, I think, is how to do a 3 by 3. I'm going to go ahead, stop share, reshare. That way I can use my calculator too. All right, so again, this is a 3 by 3. I have 3 equations and 3 variables. So I need to find 4 determinants. D, which is the coefficients. First one is -1, 2, -3. This one is 2, 0, 1. Note that the middle term here is 0 because there's no y. And 3, -4, 4. And then I'll need to find dx. To find dx, I'm going to take this x column and I'm going to replace it with my constants, 1, 0, and 2. I'm going to do that for dy. But this time, I'm going to take the middle column and replace it with 1, 0, 2. And I need to find dz. And again, to do that, I'm going to take my z column and I'm going to replace it with my constants, 1, 0, 2. These are actually not too bad of determinants to do by hand because a bunch of these zeros. But what I would do is just grab a calculator and go through and type them all in and then find the determinant of each one that way. Matrix. Edit. 3 by 3. -1. This would be a lot easier to do if I had this calculator in my hand rather than having to type it in a computer. And I'm not going to have you watch me type a whole bunch of numbers. I'll just do this first one so you can see. Once you have it typed in, remember you hit second matrix, go to the math column. First option will take the determinant. You need to tell it what matrix. And we're just going to use matrix A. Boom. First one's 10. I'm going to repeat that for these three. And then remember my answers are going to be dx over d, dy over d, and dz over d. And once you have this one, the nice thing is you can just go in and edit matrix A again and just replace the first three numbers, -1, 2, and 3, with 1, 0, 2. Right? You can navigate and just replace those three numbers and then take its determinant again. So it's not as much typing as you would think. All right, it's 8:46. You should head off to your next hour, second hour. If there's any questions, you can let me know in chat or unmute yourself right now and I'll answer them. Or if you come up with anything, you can email it to me. Okay. Well, have a good day, everybody. I'll see you tomorrow.